Okay, so t- today we're going to be having our first competitive programming beginner lectures. And the club that we're in is, of course, DSC, which is a computing tech club sponsored by Google. And our competitive programming community is meant to help you to be better at solving coding exercises that you would find on technical interviews. We have a couple of different parts in this community. Um, there are the competitive programming review lectures and the lectures for more advanced topics in competitive programming. However, this one is just for beginners. So if you're just starting off and you're trying to ease your way into, say, solving those leak code questions, solving those coding questions online, that's what we're here for. This is the easy section. This is supposed to be like a buffer. And today, we're going to be discussing, well, before we start on the lecture, we're going to be talking about time and space complexity. So this has to do with the performance of an algorithm you want to use to solve a problem. And of course, for the next couple of weeks, I think 12 weeks, we're going to be discussing various other topics in computing and, algorithms. But this is just basically an algorithms class that we're going to have every Wednesday at 3:30 to 4:45, around there. And of course, it's on YouTube right now. It's live streamed. So if you miss this, because you were busy, you can just find it. It's recorded. It's on YouTube. You don't necessarily have to take notes. I'm going to be writing on the board and explaining to you guys, everything you need to know. And also, starting tomorrow, we are going to be giving you guys coding exercises to do every day. There's going to be two different types of coding exercises. There's going to be the easier beginner types, and then the more advanced intermediate types of questions. All these questions are on LeetCode, which is, of course, I've mentioned before, but in case I wasn't clear, LeetCode is a website where they host many, many coding exercises, coding problems that a lot of people use to prepare for technical interviews, particularly in big tech companies that are, say, Facebook, Apple, Amazon, and so on. So now that we're on to that, be sure to look out for the competitive programming channel on the DSC server. Do make sure that on your role you have competitive programming to get our updates, and we'll update you of anything that goes on in our community, in our dev community. All right, so that was sort of introduction into what this course is about. So I guess we can start. I'm going to start off by talking about that's a bad Y. Time complexity. I'm going to start off with that. You can see it. All right, so you're trying to solve a problem. You're going to come up with an algorithm. So depending on the efficiency of your algorithm, it might be really slow or efficient and fast. And that totally depends on the type of algorithm you choose. So you could choose a naive solution. So that would be like for loops and things that basic solution. And you might end up with a solution that runs really slow when you encounter a big problem set or a big input size. So you need to come up with a better solution, a better algorithm, so that as the size of your problem grows, the time taken needed to solve it doesn't grow so fast. But to start off with time complexity, we need to talk about big O notation. So big O notation is basically, you might have seen, I'm going to go on this side. So maybe you've seen something like this, right? So big O is basically concerned with the worst case scenario of your worst runtime to solve a problem. And I'm going to just off the cuff, I'm going to make up a problem. So let's say I have an array, and I don't know. Okay, just an array I picked. And let's say I want to find a number, say number k equals 2. Okay? So how long do you think it could take to find the number 2 here? Well, huh? No, what do you say? What do you say?
Not long.
Well, considering the circumstances, it may not take that long. So what will you use to find a number in an array? So you would use, say, well, it is sorted, right? But let's do a more naive solution. So let's do the for loop to start. I'm going to do for I and I know I am triggering people by using Python. I definitely am. Okay. Pay no mind to that. So I'm going to choose x. So x is a number. It's the number, each number. So say x starts here. And so if x equals k, well, we found it, right? So then return true. Else, like if we go through the whole array and it's not there, we return false. You can read this? Is this okay? It's not too bad. All right. Okay, so it's my handwriting. So if we find it, return true. But if we go through the whole thing and it's not there, it's false. So well, let's say it is. Let's say it's 0, right? What about then? So it's the first one, right? So you just go to 1. But let's say it is 7. What about then? What's going to happen if I run this?
Goes through the entire thing, only to realize
It's not there. So your worst case scenario is that you're giving a number and it's not even in the array. It's not in the list. So the runtime for this, for let's say the size is n. This is size n. I know it's 6, but the runtime for this, it's O of n. Okay. I guess I should discuss, before I go further into O of n, what a constant runtime is. So say if you add 2 numbers or subtract or multiply or divide, each of this runs in O of 1. So, adding, subtracting, multiplying, dividing 2 numbers. So it's important that we say that it's 2 numbers, because that means it's a finite amount of things that we're working with. And because it's a finite amount, it runs in constant time. And what that means is that despite the size of any problem we're working with, right? This will always take the same amount of time to run. So it's going to run the same constant time. So this if statement right here is a constant runtime. So of 1, wait, that's hard to see. That's hard to see. I'm just going to put, maybe if I do this. O of 1. Okay? So the inside is O of 1, and this runs n time, n being the size of the array. So since this is inside the for loop, if you want to calculate the true runtime, we will multiply O of 1, O of n. I think this O is too big, right?
Yeah.
O is too big? Excuse me, this is I'm a computer science student, not an artist. So O of 1 times O of n, and I'm going to go from here. So the insides can come together and multiply with themselves, or add, for that matter. And then you come out, 1 times n is just n, so this is okay. So what we did was that we multiplied the inside times the outside. It came out to that. When you're multiplying big O's, you can always just put the terms inside this other big O. And then 1 times n is just n, so you come out to O of n. So the whole algorithm takes O of n to run. So what does O of n mean? O of n means that it runs in linear time. So that means that the amount of time that it takes to run at worst is directly proportional to the size of your problem. And I'm just going to put linear. Okay. So someone here in the audience, and I'm glad they mentioned it, said that because this is sorted, by the way, this can only work if it's sorted, that they could use binary search. I was going to go more into that, I think, the next lecture. But I'll briefly go into it just to see how long it takes to run. So let's say I disregarded all of this. I'm not doing a for loop. I'm going to be more creative, or say knowledgeable. Because a lot of, getting these nice solutions is about being knowledgeable about, how to solve the algorithm, so that you don't come up with a naive solution like the one we had, which was just a for loop. So there's something called binary search. Right? And it works like this, right? So we want to find number, say k. So we want to find it in this list. And I want to make it a number that's actually in there. I'm going to say 4. So to start off, we want to identify 2 variables. The left is going to be 0. And then the right, which is going to be, so the size is n minus 1. So this is going to be the last index. So while L less than R, right? And this isn't real Python notation, but whatever. So while left is less than R, here's what we do. We get the midpoint. And the midpoint is usually, it's about left plus right. Left plus right divided by 2, right? So we're trying to get the middle, which is, this is 5, 0, 5 plus 0 divided 2 is 2. So we're going to start here, right? And here's what we do. We test whether it's less than or greater than. Well, if it's equal to it, then return it. So if mid, well, actually, is equal to k, we just say, let's say we return the index where we find it. So return mid, okay? But let's say that k in the middle, k is not equal to this value. So then what do we check? Okay, so we could check the values, see if it's greater than. So if k is greater than so if k is greater than the value, what do we do? So okay, I know what you're trying to say. So basically, we cut the problem in half, right? So since k is greater than everything to the left, we cut the problem in half and only worry about everything after mid. Okay? So how do we do that? Well, we know that the leftmost value was this one. So what if we made the leftmost value the one after mid? And so you say L is equal to plus 1. Well, there's something else, right? What if k was smaller than the value of mid? What do you do? Mm-hmm. Yeah, so basically, if k was less than the mid, it's not, but say it was, we would take this portion instead. And to do that, I think I'm running out of space, but yeah, bad planning. So is less than. So if it's less than, so then you have to change right. Right has to become so it has to become mid minus 1. So right is here, this is left and right. Okay, so let's say we run this here, right? So and I'm going to change this to 3. You can see this, right? Okay. Okay. So k is 3. We want to find 3 in this list. So of course, we start off with the left being 0 and the right being n minus 1. So we get the middle. So we say that the middle is here. So is it equal to? No, it's not equal to. So what is it? Is it more than or is it less than this value? So it's more than. So that means that left now has to be the one right after mid. Okay, so now we changed left, right, and see now the problem was cut right in half. We are now only looking at half the problem versus looking at the whole thing. So then we get the mid, which is just 5 plus 3, yeah. All right, so mid again. So k is 3. Is it equal to 4? No, it's not. Is it less than, greater than? Okay, less than. So then that means that R has to be here. Okay. Actually, now that I think about it, okay. So now they're both the same, right? And the average of, both numbers being the same is just that number. So now, this is the middle. It's a bad M, but whatever. This is the middle, it's 3. So, K, is it equal to 3? Yes. So now we return this index value. So I want you to take notice that here we cut up the problem such that we don't have to look through every single value in the list, in the array. And this took some knowledge, but because we knew about this, we were able to find a more efficient, a better solution. And the runtime of this is O of log n. So log n is, logarithm. And I'm going to erase, get a good look at this, because I'm going to erase this. It's on YouTube, so it doesn't matter. Okay. Erase this too. So let's say Rn, we had a set of n's, so I'm going to start with 2, and from 2 I go to 4, from 4 I go to 8. All right, and let's log. So to be clear, n is the size of your problem set, your input. So let's say you had 2 arrays for and they were a list of these many numbers, right? And they were all sorted, and you wanted to find the value in it. So how long would it take? Well, since binary search is O of log n, we could actually see what the worst case scenario is by actually just plugging it in. So what's log of 2? Okay, I'll just say. So log of 2, well, also, since it's binary, it's in base 2. So that means it's 2 is being raised to this power to get to this number, okay? Okay, so what about here? Okay, yeah, 2, and here, and then 3, right? And then this one, yeah, okay, yeah. I think you all get the idea. 6, all right. So again, this is the size of your problem, and this is the time, the worst possible time it could take to solve it. So notice how the problem grew exponentially. Like, see, it went from 2 to 4 to 8 to 16, 32, 64. But here, down here, it grew linearly. So the time didn't grow as fast as the size. This is beautiful. I mean, that means that this time taken to solve your problem, he's over there reacting. It is beautiful though. It is. It is. I don't know what you're laughing at. But but anyway, so see, and in the function, let me put it over here, right? So let's say this is time, this is n. So let me go with this one. This is O of n, like before, our naive solution. And then our O of log of n it doesn't go down. It does not go down. I think that's good. Doesn't grow as fast as the other one. So that means that if in the other solution, the for loop, we had 128, and we had to do we had to go through all 128 values. Versus in binary search, it was O of log n. So we really only have to look for 7 values. And that was the advantage of using binary search versus using just naive brute force searching. Now, of course, it can only work if it was sorted. If it wasn't sorted, binary search just is useless. Okay, so I came up with a problem in my head the other day that we could work with. To show you that having like math knowledge does help with solving some problems. Let's say I wanted to find, we have an array, and yeah, it's going to start from 1 this time. 2, 3, 4, 2, n. All right. I'm not going to say what n is. I guess we can just say, for now, it is 10. All right. So we have an array of numbers, and here is what I want you to solve. I want you to get, for each index, the sum of every other number except for that one. Okay? So, example would be, this would be 2 plus 3 plus, I guess, 10, right? And here would be 1 plus 3 plus 10. All right. So what do you think we could do to solve this problem? Yeah.
Remove the number you're looking from before in the array, and then just go through the array that you just made without the number.
So just basically have another for loop inside and say add all the numbers after it, or all the numbers except it.
I think just make like a copy of the array and then alter that one.
You mean just, well, that's going to be, well, we could do that. But why don't we just not have to make a copy to save space? So,
Is the formula the...
hold on, no. We'll get into it. We will get into it. I know you know what it is. Yes, it is that what you're thinking of. It is that. So see, it takes math knowledge to solve this efficiently. Okay, so what you were saying is just basically add all the numbers, right? So what if we had like a nested for loop to do that? Let's say we had solution 1, right? And we just say for x in R, for y in R. Well, actually, print. Okay. So this is one thing I would think. Yeah, go on.
Wait, fun fact, I got asked this question in a Google interview,
Oh.
like when I first switched to CS, and I did it exactly like you just said.
Yeah.
You didn't get Google, so it wasn't good. I didn't know the formula.
So yeah, Lazo just said he did a Google interview when he switched, and he used exactly this. Well, I mean, what Hermes was saying. He didn't get it, but that's okay. That's fine. Yeah, yes, it is. It's fine. You were too good for them. I mean, wait, we're a Google club. Never mind. I'll take that. I'll take that back. Thank you, Sundar.
Yeah.
Yes, we are gonna edit.
Now I have to.
No, no, you don't. I love you, Sundar. There. That's it. I made up. So, back to this. We're not memeing anymore. We're serious. So, what's the problem with this?
The time complexity is way too big.
That is one thing. So, what we're doing is basically this, right? And I'm actually gonna write out the whole thing. I'm actually gonna. Am I gonna have enough space? I'm just gonna say that it goes up to 7. 5, 6, 7. Yeah, I think we're gonna have space for that. 2, 4, 5, 6, 8. Wait. 7. Okay, my arm got tired. Okay. But the reason why I wrote it out like that, like the whole thing. You see how long it took me to write out all that? Your computer is basically doing that work, right? So I know that for each element in the array, we have to get a sum. So we have another for loop that adds all of the numbers except for, the one we're at. We calculate it and then you print it. Okay. What shape is this? More or less. Yeah. What shape is it?
Like a matrix.
Well, yeah. It's a square, right? So it's like a matrix. So how many pluses did we do? I know it's kind of cheesy, but I wanted to draw it out.
Okay.
How many pluses do we do? How many adds? 1, 2, 3, 4. Is it 5? Is it really 5? Yeah, I guess it is.
You can start from there.
No, I know. But actually, I did that on purpose. I wanted to start from 1 for the sake of the math formula that we're going to use. But you see, this took so long to do, right? And if we knew the big brain formula, we didn't have to do all this. So there is this math formula. So I did make it so that it goes from 1 to, say, 7 here in this case. So let's say it's n. So this is, what if at first we added them all together and then we just subtract that number by this, right? We could do that. So we just do, write it down. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. And that is 7 times 8, 26, 2. I'm doing it in my head. 27. This is 27. Okay. I was also trying to use the formula in my head too, but it became easier. Okay, so this is 27. And then we store that number somewhere. And then for each of these, we just subtract 27 from this, and we print that out. And so this is Doesn't look like a 1. There, that looks like a 1. I'm gonna erase this. So say goodbye. So first, well, I'm just gonna put like, is it 28?
You forgot one number.
I did, right. 56 divided by 2.
Yeah, that one too.
Yes, okay. So thank you for correcting me on that, because I would have. Yeah, I did it on purpose to see how smart you all are. So say S is the sum, and I just used the Python sum. I just wanted to get that. And so for X, and we say S minus X. Okay? So this, when you do it like this, you learn all this. Instead of doing like so many pluses, n squared pluses, you do minus 1, 2, 8 minus 4, minus 5, 8 minus 6, 8, and 7. All right. So instead of doing so many additions, we just have to do a linear amount of subtractions, right? And that's all we had to do. So this takes a lot less time. All right, take it easy. Yeah, no, thank you. Thank you for coming.
Absolutely.
So now instead of doing so many pluses, we only do a linear amount of minuses. Could we improve this? Could we improve this? Yes, with the formula. With the formula, right, that I was going to get to, I'm getting to now. So there's this formula in calculus, right, such that I think this is starting this I, right? It's like this? I think it's like that. I think it's like this. It's been a while. So, yeah. Right, so this is sigma. This is the Greek letter sig. I'm in the screen, right?
Yeah.
Okay.
Yeah, you are, yeah.
Okay.
Well,
This.
you're not, but the thing is-
Okay. Well. Okay. So that's what matters. So this is sigma. This is the Greek letter sigma, which in math we just say that's sum, right? Because S. So Okay.
Because of S?
Yeah.
That's
Yeah.
why? Okay.
Okay.
I
That
didn't
was
know that. Thank you.
that was a joke. That was a joke, and it worked. I don't know if you're laughing with. I don't know if he's laughing with me or at me.
No.
No. We should turn the camera on you. You should turn the. You look red. You look like un tomate. All right. We're getting distracted. Okay. So sum of this is 1 plus 2 all the way to n, which is the term. This n right here is a terminating, and this I equals 1. This is the initial value. All right. And there's a formula for this where we don't actually have to do n additions. We don't even have to do that. Because it turns out, using some fancy math, this is equal to n times m plus 1 divided 2. So, what if we just use that? We use that formula. So, instead of s equals sum array, let's say s equal the formula, which I'm just going to call formula. Let's say does that. Okay. So what's the runtime for this addition? This one right here. Is it n squared? It goes from 1 to n.
Linear.
So this is linear. Because you're doing n additions, a linear amount of additions. Now what about here? Well, this is n squared. However, um, to calculate this, how long does this take to get the number? Constant, right. So to calculate this is constant. So instead of having a sum that was linear before, we could have this formula, and we sped up the problem even further, right? I mean, you still have to do all of this, but you save yourself an extra for loop. And that's what makes this one superior to the other one.
Okay, I don't mind a meeting when I don't understand something, so then you go over that again.
What do you mean?
Why is it linear?
Why is this linear?
Linear, no constant, the formula.
Okay, so this is to calculate it. This is to get the value, right? Because that is the same as it's n times n plus 1, right? So what is addition? Right. So you get some constant value. Well, okay, that's going to be confusing. I'm going to leave it like that, okay? Okay. So this is, addition is constant. What is division? Right. It's constant time. And then you multiply it, it's also constant. So that means the time it takes to run this is not the same as running n, additions. That's why this is better. If we just have this fancy formula to calculate what the sum is, considering these circumstances. Does that make sense now? Okay, you're confused still. You're confused still.
Okay, I will talk about 5 a.m.
Oh, yeah. I gotta get that rest. So, you wanted to ask something?
So we can generally say that arithmetic and checking two things are equal to each other, or if one is greater than the other, that it's equal, it's constant.
What do you? Well, I mean, if we add all in the arithmetic, to do that many addition takes time.
Yeah.
It takes a linear amount of additions.
So, outside of a for loop. Okay, so no, even if it's inside the for loop, it's still constant. It's constant. But things like that, for simple math like that, when adding one thing to a variable, that's generally constant time.
Right. Yeah. When you add or subtract from a variable, that's all constant time. It's not dependent on any size of any input.
Yeah.
Right? The computer's just gonna do that math instantly. I mean, more or less instantly. Yeah.
So is the reason that the formula better, the reason that it's better than the adding one to
Yeah.
another, is it because it stays 1, 2, 3, 4, it stays 4 numbers and the same amount of multiplication, addition, division?
Wait, what do you mean?
It's not increasing in size.
Right. So this is so
Stays.
so n, right? Okay, I didn't say n is a number, right? And we save that number as the size of this. Okay? It's a constant. It's a constant number. And to multiply a constant times another constant, divide by another constant, that's not going to take n amount of time. That's going to happen instantly.
I got it now.
Oh, okay, you got it now? Was it this? It was this. The magic snap. But yeah, that's why to do this, it's better than to just adding them all together. So, also sometimes you may make silly mistakes where I'm gonna put silly where let's say we disregard the formula. And let's say instead of putting so we'll go back to sum. Right? We go back to this where we do add it. And let's say by accident you put it in here. Let's say you put the sum there by accident, and I'm going to comment that. Oh, that's a Java comment. Yeah, it's a Java comment. It's a mix of Java and Python. Oh, whatever, whatever. So technical. I'm satisfying everyone. See, I'm satisfying you. You know who I'm talking to.
Okay, I thought you were
You-
looking right at
No,
me.
not at you. I'm talking
Okay.
to you, to the camera. Okay, so let's say the sum we do it in the for loop instead of outside. What's gonna happen then? Yeah, I mean,
So the sum function is going over the whole array, right?
yeah, but you do it the length of the array times.
Oh, you want to say that the time complexity?
Yeah, yeah,
Oh,
yeah.
n squared.
This is n squared. Do you see why it's n squared? Because, making sure I don't trip over this. This is O of n, right? But the whole thing is O of n. And remember what we did before, right? You can multiply what's inside times what, holding it in. So and that I'll just do it here. Okay. You see that? It's impossible not to see. It's big. I know. I write pretty big on the board. So because we did an n, a linear operation inside another linear, it made it quadratic. So if you make a silly mistake like that, that's going to, eat up your time complexity. So be sure not to, debug properly. Yeah.
So when we had it previously outside of the for loop,
Yeah.
where we did the sum outside.
Yeah. Okay. So let's say we did it outside, and I'm gonna comment this one out. Okay. This is O of n. So now, because it's outside, and this happens before this, right? This is independent of this. It's not times. It's going to be plus, right? And this is going to end up, I'm going to write it here. We go of 2n. But see, in big O notation, the coefficient 2, that would just be wiped out. So it'll be O of n, right? So it's back to being linear. And that is not a silly solution. It's not a silly solution at this point. No longer silly because, we erased that mistake. Okay, how are we on time? 4:23.
You've been doing this for 52 minutes.
I have. We haven't. Yes, you're right. We have been doing it for that long.
Wait,
I think. What?
no, it's fine.
Okay. All right. You didn't have a question. So, I think that's just the basics of that. There's also exponential that I briefly want to get into. Okay. Really quick, where is it? Just to finish that function, that's O of n, that's O of log n. And O of n squared is one that grows much faster. Oh, but that's too much of curve. That's too much curve. Okay. And that's the graph up to n squared. And there are some that could be O of n cubed, O n to the 4, O n to the 5. But a worse one than that is 2 to the n, and that's exponential. And I guess I'll give you an example, say exponent 2, right? All right, so let's say, and we want to calculate 2 to that exponent, right? But we want to use it with addition. Why? I don't know. Because I'm trying to show you what exponential time is. So we're going to do this recursively. So in recursion, we have a base case. If n equals 0, return 1. 2 to the 0, anything to the 0 is 1. All right? But if it's not that, then we return, recursively call it again. All right. So what does the tree look like for that? The whole recursive tree. Well, first of all, what's happening here?
You're waiting that it goes through the entire recursion process by having like checking that it's not 0.
Well, see, we're checking that if it's 0, we return a concrete value. We don't call recursion again. This is our base case. This is what ends recursion. Once we reach here, we stop recursing, and that's it. But if it's not 0, then we recursively call the function twice. We add them together. Okay. I'm gonna give you proof that this actually does work. 2, 3, right? It should be 8. It should be 8. So what's this? Well, in the recursive tree, right, it's going to be 3 minus 1. That's 2. 2. Next 2. 2, 1. Okay. And then x2, and it goes to 0. And we know that if it's 0, it's just 1. And we're adding, right? And then it's 1 plus 1. 1 plus 1. Right. And obviously you want to add everything together. Okay, so it's 1 plus 1, that's 2. Plus 1 is 3, plus 1 is 4, plus 1 is 5, 6, 7, 8. So this actually gives you the solution by adding everything together. But because we chose to add everything together, it takes really long. It took 8 amount of time. It actually took an exponential amount of time for this to run. What if this was 100? What if it was 100? How much would you have to write towards the end? Yeah, 2 to the 100. So that would be 2 to the 100 depth, and then you would have 2 to the 100 ones that you have to add. Yeah.
Maybe show them like how depth is 2 to the level.
Right. Okay. So, well, actually, depth is n, but the leaves. So the depth is n, but the amount of leaves you end up with is 2 to the n. So you're doing 2 to the n operations. So that's why this takes 2 to the n times to solve. Is this confusing yet? You're confused?
Yeah.
Okay. Okay, all right.
You're assuming that I know recursion.
Oh yeah. So recursion means that you're calling the function. The function is calling itself. And the idea is that when you call itself, it's going towards the base case so as to stop calling itself. Because see right here, like it was calling itself up until it returned 1, right? So it could actually return, a solution. Maybe does that kind of make sense?
Yeah.
Yeah? Okay. So the depth is n, but the amount of operations is 2 to the n. So that makes this, it grows very, very, very fast. And I'm going to draw it here. I don't have that much space to be 2 to the n. So bad runtime. Also, I know we don't have a lot of time, but we really don't, but I'm really glad we talked about recursion, right? And the reason why I'm really glad is this, right? When a function recursively calls itself, it's adding to the stack, right? So we got RAM, which is a computer part, and when a function, say xb2 calls itself, it's adding memory to the stack. And it keeps calling itself, and it keeps doing it. And what if the recursive depth is so large, you run out of memory? That's going to be a problem. You can't do that. Then that's going to be a space complexity issue. Of course, space complexity is more than just, the recursive stuff. There's also the issue of auxiliary memory data structures. So auxiliary data structures. I'm going to leave that like that. And I'm going to erase this. We have 10 minutes, Laz? Maybe more?
Yeah, we have one. We've been doing this for
1 hour?
Yeah.
We have 15 minutes. Okay. Okay. We have some time. All right. So, well, you were saying before you were going to make a copy of the array. How much extra space would that have been?
Sure, an extra array.
Well, in terms of big O.
Constant.
Are you sure? Creating an extra copy of the array? Well, what's the size of the array?
N.
So what would the size of the copy be?
N.
So it would be a linear extra memory data structure that takes up memory. And an additional auxiliary data structure that takes up memory. So some solutions you don't really need to make an array copy. Sometimes you could just work with a constant number of variables. Let's say Fibonacci, right? So f1 equals 1, f2 equals 1, and f of n equals n minus 2, 1, right? Now let's say I wanted to calculate f of 7, right? What do you think we should do? What's one thing we could do in terms of auxiliary data structures, auxiliary memory?
You just store two values at a time.
You- Well, we could do that. Well, we could create an array, right? A fib array. We create an additional fib array. Because at first we're just given these two values and that rule. We can create a fib array of size n. So n being 7 now. Uh, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay. And you just keep filling them up. So this is equal to these two added together. Okay, then you can fill this one up. It's these two added together. This one's equal to these two added together, and so on. And then you just pull that extra data structure, right? Okay. Well, we didn't need to make another fib array. We didn't need to do an array. We didn't need to make an array because making an extra array would have been O of n space complexity, right? So this is So it's O of n space complexity because you need an extra data structure to have n variables. And what I'm saying is that to solve for the fib number, you don't need this. You don't need this array at all. You could solve it using two variables. And notice that I said 2. I didn't say n or anything. I said 2. And that's important because 2 is a finite number and 2 is equal to O of 1. Is equal to constant. It's a constant number. So instead of that, we could have like, I think it's x equals 1, y equals 1, okay, and z equals, I think it's 0. And then I equals, we're going to start with 3. Okay. If I'm mistaken. Okay. I don't remember if this is exactly, I just came up with it, but this is the solution. So here's what you do, right? You make x and y equal to, x equal to fib 1 and y equal to fib 2 and z equal to, well, it doesn't matter at first. The point is that you start from I equals 3, you go to 7 or n, and then z equals the last two, right? And then x equals, or y equals, before, and then y is going to equal to z. And why is that? Why are we doing this? So we're adding the previous ones here. We're adding the previous values, and then we're updating the values x and y for the next one, right? And that's what's happening here. So x takes the place of y, and y takes the place of whatever the addition was. And then when you're done, you just return negative y. Is it y? I think it's y. It's either y or z. I mean, they're both going to be equal to the same thing. And then once you get to that point, you're pretty much done. You return that. See, you didn't need an extra array. You could have solved it with 3 variables. And since 3 is a constant number, it's O of 1 constant space complexity. I didn't want to write the whole thing. All right, yeah. Any questions about this? No? It's clear why this is constant? Okay. All right, and how are we on time now?
Okay, you're fine,
7 minutes? Okay.
Maybe you want to talk about whether we'll see next week.
Okay, so
If you're done.
I mean, I don't really know what else to talk about now. I mean, we went over both space and time. I mean, if I go further, I'd be talking about the next lectures, couple of lectures. So I think I'll just say for now, let me pull up the itinerary, because I don't have the exact schedule next week. Let me pull it up right now. Okay, so we just had our time and space complexity meeting, which was just this. And the next 2 meetings, we're going to talk about arrays. A lot of things concerning arrays. We kind of just touched upon it now, I know, but this is like the buffer meeting. So this is just like the first meeting. So we want to get time and space complexity. We want to understand it so that we know how an algorithm performs. So when I'm talking about time and space complexity in the next lectures, we're up to speed on like what we're talking about. So that's what this was for. So next meeting is arrays. We're gonna talk about like sorting arrays to start. All the different sorting algorithms. That's the first. And then we're gonna talk about binary search again, different array kind of data structures like stacks and queues and their uses. And then we're gonna talk about recursion again, which I know we just talked about. We're gonna talk about Fibonacci again, factorial, a little bit of memoization. It's a little bit complex, but it's not too hard for the simpler type of problems. Then we're gonna talk about linked lists, and that's 2 meetings. Trees, that's 3 meetings. We're gonna discuss graphs, and that's gonna be 4 meetings. So a whole month is dedicated to graphing algorithms. I mean, yeah, and that's pretty much what we have for the next 12 weeks. We may add more to the lectures if we have time. But yeah, I think that concludes this lecture. Thank you for coming personally and for watching this live stream on YouTube. We appreciate it.